to our next lecture. We want to continue our consideration from last time, yesterday. But at the beginning, I have somebody here, a former PhD student. Sounds crazy. Who wants to make an announcement, and therefore I directly hand over to Dr. Jairo.
Thank you, Professor Hohmann, for the introduction. Well, first, I thought I can present this in English. Dann habe ich mir überlegt, hier können wahrscheinlich die meisten Deutsch. Also werde ich das doch auf Deutsch vorstellen. Ja, also mein Name ist Jairo Inga. Ich war früher wissenschaftlicher Mitarbeiter am IRS. Deswegen freut es mich umso mehr, hier auch vor euch hier stehen zu dürfen und euch ein bisschen was zu präsentieren, die Werbetrommel einrühren. Und genau, worum geht es hier? Es geht hier um eine Praktikumsstelle. Ich habe schon von Herrn Klube gehört, ja, das ist eigentlich gar nicht mehr Pflicht. Deswegen muss man halt gucken. Genau, aber was ich hier jetzt sagen möchte, ist, dass es auf jeden Fall eine Top-Gelegenheit ist, in die Industrie einzuschnuppern, da zu gucken, wie läuft es überhaupt zurzeit in der Softwareentwicklung in so einer Firma wie Mercedes, wo es um automatisiertes Fahren geht. Und vielleicht würde der eine oder andere denken, ja, aber hey, Fahrassistenzsysteme, automatisiertes Fahren ist irgendwie doch alles schon längst gelöst. Was gibt's dann überhaupt noch zu machen? Tesla macht die ganze Zeit und also ja, und die Antwort eigentlich drauf ist, es ist gar nicht so schon gelöst, wie man denkt. Also man sieht ja auch, die meisten Systeme sind teilautomatisiert. Also das heißt, man hat als Mensch trotzdem die volle Verantwortung dafür. Also da gibt es noch viele Sachen, die man vor allem um Garantien zu geben. Das ist zentral, um wirklich den Schritt von teilautomatisiert auf hochautomatisiert zu gehen, also Level 3 Systeme. Und in diese Richtung gehen wir bei Mercedes-Benz zusammen mit unserem Kooperationspartner NVIDIA, der hoffentlich auch ein Begriff ist für die meisten von euch. Wir arbeiten nämlich zusammen in einem Projekt um die nächste Generation von automatisierten Fahrzeugen rauszubringen, auch auf den Markt. Und bei dieser Praktikumsstelle geht es genau um die Mitarbeit bei sowohl dem Projekt, was noch läuft, zusammen mit NVIDIA, aber auch für die zukünftige Generation von automatisierten Fahrfunktionen, was auch mit NVIDIA sein wird. Das heißt, es ist eine spannende internationale Kooperation und ich glaube, im Praktikum ist es, ja, da gibt es die Gelegenheit, wirklich da zu merken, ja, wie läuft denn überhaupt sowas? Was gibt es da für aktuelle Herausforderungen? Und natürlich sich auch als Regelungstechniker oder Regelungstechnikerin auch einzubringen. Deswegen bin ich auch hier, weil, also ihr habt es vielleicht schon gesehen, worum geht es? Es geht um Simulation und Implementierung von Regelungsalgorithmen. Die Aufgaben umfassen auch die Teilnahme an Versuchsfahrten. Also aber bei unserem Team ist es nicht so, dass wir programmieren und dann abgeben und sonst wissen wir nichts von der Welt, sondern wir sitzen auch selbst am Fahrzeug, dürfen fahren, dürfen testen und wirklich das erleben, was wir gerade programmiert haben. Und natürlich dazu gehört die Analyse, die am Ende kommt. Ja, und warum bin ich hier? Weil ich finde, dass ihr schon mindestens die 2 ersten Anforderungen schon erfüllt, nämlich seid im Masterstudiengang ETIT oder MIT. Vertiefte Kenntnisse in der Regelungstechnik. Vor allem suchen wir Leute, die mit dem Zustandsraum etwas anfangen können. Und natürlich auch Erfahrung in Python, also Objektorientierung sollte ein Begriff sein. Was eine Klasse ist, sollte das Mindeste sein. Und ja, Versionierung mit Git ist auch unser alltägliches Brot. Und natürlich Interesse an der Softwareentwicklung. Wenn es für euch grundsätzlich interessant klingt, würde ich mich sehr freuen. Das hier ist so eine Art Pre-Sale. Das heißt, das ist noch nicht ausgeschrieben. Und wer ja aber Interesse hat an der Stelle, bitte, das kann man leider nicht so gut sehen, aber doch, die E-Mail-Adresse kann man sehen. Also Jairo Inge ist mein Name und da ist meine E-Mail-Adresse. Einfach eine E-Mail schreiben und sagen, hey, ich habe Interesse, könnt ihr vielleicht noch ein bisschen mehr darüber erfahren oder einfach, dass man in Kontakt kommt. Wie gesagt, noch außerhalb von der offiziellen Ausschreibung. Das heißt, wenn ihr Interesse habt, nutzt auf jeden Fall die Gelegenheit und ich würde mich sehr freuen, jemanden aus dem KIT und speziell aus dem IRS vielleicht doch als Praktikant oder Praktikantin begrüßen zu dürfen. Das war's und danke für die Aufmerksamkeit und ich wünsche viel Spaß bei der Vorlesung.
Here, now the micro is on, but strange. Okay. So hopefully you can hear me right now. And in addition, we should check whether we can restart this. Let's see. It works perfect. So I try. Usually I see a frame, but it's not present. Strange. So perhaps we do the following. No, it should be present. Okay. Again. Now. This sounds great. Perfect. There we are. Okay. Hopefully everything is online right now. Okay. This is the setting. And as last time, I forget to switch on the micro, then nothing is transmitted, obviously. That's the problem. Okay. Now let's see how it can go. You remember the Newton direction, the Gauss-Newton method, and also other things, and the Levenberg-Marquardt direction, something which we talked about in ODS. These are well-known results, but we want to look at the linear least squares problems first. You should have heard something about that in the bachelor degree lectures, right? So everybody, you should. So I learned yesterday evening, I watched TV and saw a discussion about the future school system, and they complained about that the pupils are answering the question by using ChatGPT below the table and directly during the lecture. And I thought, why not using that here? It's a good idea to use and to implement these large language models in our daily business of lecturing something. So least squares. So as a hint, what happens there? Who remembers what is least squares about for linear systems? Perhaps this is the early age starting point. Gauss said already at the age of 18. This is always a little bit strange, but he wanted to observe the trajectories of the planets, and therefore he was well aware that there is the atmosphere who's shifting his observation on the one hand, and also his personal problems with holding the instruments in a way that he gets good observations. And the problem at that set is that we want to fit a linear model, which is given here. So yk is represented as a set of parameters, theta m, multiplied with the input values, so the measurement values. And k indicates the value itself. So if I have one measurement, I can associate the output with the input. Of course, university speaking, we not just look for one measurement with one input variable. We look at a set of measurements, and this so just a whole bunch of measurements at one shot, and one input measurement as well. So So we have a multiple input, single output system. For simplification, it also generalizes to multiple output systems. But to keep it interesting, we have multiple input system. So we assume further that the real static system, this is just an assumption. We do not know that, right? If you have a black box, it's a black box. You don't know anything about it, but we can assume something. And if I'm allowed to assume, I assume it's linear, okay? So should be a linear setting. So the real static system is linear as well. And the only thing which might affect our problem is our disturbances. And the question is, how good are we in representing the real system? That's something which drives us. And probably you should have heard of the various results. So the setting is a little bit similar to what we discussed before, but now the real system is linear. The model system is also linear, and we adjust via an optimizer the parameters here such that the parameters theta m fit theta. So the original parameters are the real parameters of theta, and theta m are our estimated parameters in that sense. And we try to do this by just minimizing this deviation between the real output and the predicted output ym if the same input values are feed into our linear model, right? That's the setting. Okay, now let's do a little bit math. If the measured output is given by y1 and yn, so we have capital N measurements, and n should be sufficiently large. We talk about this, how large it should be, but at the very beginning, it's sufficiently big number. And we have input quantities, and now it becomes a little bit strange. So row by row, we have one measurement for inputs. We have P input values and capital N measurements, obviously, right? And now what I do, I put everything in a super matrix because it helps me to describe the entire measurement setting. So if you read it row-wise, theta 1 up to theta p1 times theta, u11 up to up1 times theta gives y1 and so on. So that's the setting. So our model output for all measurements given here is calculated by means of the matrix U, which includes the inputs times the unknown parameters. That's the setting. And the question is how to get the border parameters. Okay, I said we build the output error, okay, and with the output error we sum it up, we square at the output error, and with that we get our result. So in a setting like in ODS, we use a half E transpose E. This is the summation of all errors, which is similar to say a half Y minus YM transpose Y minus YM. So again, the deviation between the model prediction and the output setting, which we measured. Ym then is calculated by means of theta m times u. Again, nothing else as the model prediction, what we find here. And last but not least, with that, we know if you look at this, the unknown variables are theta m parameter sets. And if you carefully watch and carefully look at the problem, what do you see in terms of the mathematical structure of it? Is the objective function linear? First question. No. Is it nonlinear? Yes. If it's not linear, it's nonlinear. Perfect. Thank you very much for helping me. Next, it's a specific one, and therefore it's important to see kind of nonlinearity do we have here. So roughly, grossly speaking. Yes. Quadratic function. Yes, wonderful. So why are quadratic functions so nice? Yes. Oh, perfect. Yes, we have a convex function. So we have one optimal point, exact. And a second, what we know from ODS perhaps, if we use, yes, please. Newton works perfectly. So let's apply the Newton algorithm directly, because why? What is meant with perfectly? Yeah, please. One step. So I do one step and I'm in the minimum. So, and that's what I did. I apply Newton. It's, by the way, it's set here on the slide. But that's why interesting. And here we get the result. So if I apply Newton, what is meant with Newton? You just use the Hessian calculation of this. And if you remember, you can do it at home. Look at the Hessian calculation of the slide before. You will end up with the following setting. So it's quite simple. You take the U values, do some matrix manipulations, which are indicated here, multiply with Y, and you get the optimal parameter setting. That's it. And it's interesting to see because the matrix U, usually when I was a student, I always thought of matrices being quadratic. So rows and columns have the same size. So always, if I think of matrices, looked in my head like a quadratic matrix. Be careful. So it must not be the case for me. It was the case at that point, at that time. But here it's not the case. So U transpose has usually sufficiently more rows than columns. So look back here. The number of measurements define the number of rows. So you have it's more like a huge building, right? So to put a picture in your head. So like a skyscraper. So it looks like that. If you have 1,000 or 1 million measurements, you have 1 million rows, and that's it. And if you think of 1 million rows matrices, you get, it's not so nice. So you need to multiply a matrix with 1 million rows and perhaps with a matrix with 1 million columns. And that is perhaps a little bit difficult for hand calculation, but for a computer program, it's really not difficult. On the other hand, the more input variables you have, the more difficult the inverse might be to calculate, and then you have this matrix manipulation. But overall, it's just as simple as that. And this particular calculation here, U transpose U to the power of -1, U transpose has a name. It's called, according to their inventors, Moore-Penrose pseudo-inverse. Of course, U transpose U is of dimension PP, so P number of columns, and it must exist. Does it always exist? If you do measurements, so your input value, so this is the U matrix. You have U transpose times U. Is it always, gives it always a invertible matrix? If I ask this way, no, obviously not. Can you tell me one example where it's not the case? The most simplest one you have in mind. Exactly. So if I take, for example, just zeros, if I do not input anything to the system, now I transfer this in your practical world. Going back to this example, if I do not enter something to my real system, I cannot expect to get something out of no measurements. That's the language version of, or the text version of what has been discussed in mathematics. So put zeros in it. So entering zero into a system and try to get the parameters out of it is obviously something you can get, you can imagine wouldn't work. Second, if you always take the same values as you said, is also not a good idea, because we cannot expect that if we enter the same values into the system and get some information out of the system. So obviously, making a million times the same measurement is not the best idea. Should somehow vary the input values. How we should vary the input values is a different story. We come to this later again, but we should do this. If not, you get no information out of it. And this is called, oops. We should excite the system sufficiently well. So if I ask my little boy, he excites the system by smashing against it, and then I see, okay, it's falling down, and I see how it works, right? That's the very same thing. So try test signals are the right word for this. Test signals at the age of 6 is different to test signals for you, of course, but sometimes not. Second, of course, you need more measurements. That's also clear. More measurements than parameters you want to identify. It's also clear, I think, this from a mathematical perspective. Okay. Here, as a recap, you can also do these hand calculations to find the solution by just deriving and find the zeros of the first order derivative. And then you can prove that's the minimum. That's also possible, of course. That's what is here on the slide. Now I come back to my first question. The question is, if I do it that way, I minimize the errors. Do I get the right parameters? So again, in our picture. So if I minimize the sum of squares of these error values, do I get the parameters, by minimization, do I get the right parameters, meaning that theta m fits to theta? If we have some sort of disturbances here. That was the setting. And yes? That's the interesting fact. So why did Gauss use this method, by the way, to find the right parameters for the planetary motion? The answer, under certain circumstances, we get the right parameters, and we want to check under which conditions. But the first question should be, what is meant with right? Right? So, so we cannot expect to get the right parameters if I do something really weird at the output, and therefore you're right. So the question is, what do I mean if I speak about right? So first of all, we can say, okay, the disturbance is some sort of stochastic interference on the output, which is just added. And then we can call the right parameter setting as such if the expectation value, so the expectation over all possible disturbances, so our stochastic variable E, which epsilon, sorry, which enters the output, affects the output, but the expectation is equal to of theta m is equal to theta. So if I look at all a certain distribution, do I get the right? This would be one notion of saying yes, it's right. But I would say, no, that's not sufficient. Why? Because are you right with an expectation? Would you be happy if that's just the expectation of a variable is equal to the right variable? What could happen also? It's a question for you. If the expectation is equal, you get more or less in the mean the right parameters, yes. But what can happen? A little bit about stochastics knowledge. The mean value is exactly the same. So taking the expectation as being the mean value, yes, it's the same. But can you be happy with that? Please feel free. The variance, exactly. So are you happy if the variance of what can happen with the variance to further ask the questions? Hmm? Exactly. And so I'm not happy if I have in the mean the right value, but I have a super huge variance. Because I can't be sure that the expectation, if I have a specific measurement, a specific result, I can't be sure to get at this moment the right result because we have such a large variance, and therefore I'm not happy. I should have something else. Therefore, very often a different notion of um, good or right estimation is given by means of consistent in terms of consistency. Have you ever heard the term consistency of a yes? Okay, so it's just a recap here. A second notion of having a good estimation would also be the following. If we compare our model parameters, which we just estimated, with the right parameters, there is a probability tending to zero the more measurements I make, the more estimations I have tends to zero. There's almost no probability to have a deviation. This makes sense, isn't it? There's an interesting fact we can prove or define as follows. We get a consistent estimation in the mean square sense if it is bias free first, and second, the variance of the probability limit of the variance tends to zero over the number of measurements. And that makes sense, right? So for us, you can prove this, not so important at that point, but it helps to define what we mean if we are happy or not. And it's right out from our textual definition of what we would expect when I'm happy to get a good result. So this is the idea behind consistency, and we want to use it for our definition for our least squares problem for linear system. Now we consider a disturbance epsilon k for each measurement, and then the following proposition can be proved. First of all, we assume that these matrices exist and the inverse exist and all other things. Then the parameters of a linear static system are estimated consistently in the mean square sense if the input UK is uncorrelated with the disturbance. So if the input does not interfere with the disturbance, and second, either the expectation of the disturbance is zero, or the expectation of the input values are zero. That's it. So then we get consistency. That's an interesting fact, and this answers your question. No, first of all, be careful. It's just it and one if. It's not if and only if. It's just if. So if this holds, then everything is fine, but it's not only if, but if we have this. But you're right. So if I do something weird with the disturbances, I cannot expect to get a consistent estimator. Well, you can check whether this is true. For example, if, for example, this here is equal to some positive value, always 5 volts are added to the measurements. Well, you will be always biased by 5 volts, and you never get the right parameters, obviously, right? This directly interferes the values of the parameter setting first. But on the other hand, if we can fulfill or ensure that the variance is equal to 0, or our excitation signal, so the input is always fluctuating around a 0 value, then we can expect to have a consistent estimator. So we should make as much measurements as possible, and then we can be happy. So the answer is yes and no. So you're right. And on the other hand, Gauss was also right, because he thought when measuring and shivering around with his instruments that he always has just a fluctuation around 0. And the atmosphere also does not bring some bias into it. At the very end, this is not entirely true as far as I know, but overall, this is something very interesting. So what we get out of this is, yes, we get the right parameters, and we should be sure that this happens. Do you know a signal which helps us to be uncorrelated with the disturbances? So in the input, again, the question perhaps was a little bit too condensed. The input can be chosen by you, right? Because you excite the system, you want to get information out of it. We learned, okay, always setting it to 0 is not a good idea. 1 is also not a good idea. So the question, what is a good idea as input signal? And here we get an indication what are good input signals. Should be uncorrelated with the disturbance. Which kind of signals helps us to be uncorrelated with other signals? Do you remember that, perhaps? So a signal which should not have to do with other signals, just as a hint. Yes, white noise. Why not white noise? What is the specific property of white noise? Almost every other thing. It has certain properties. So white noise, first the signal itself, it's uncorrelated with the next value of itself, right? That's the definition of white noise. So we can expect that it will be uncorrelated with another signal as well. So therefore white noise is good. There's one exception. If you use the same if you have the same white noise as disturbance, then obviously it's correlated clearly. But in all other cases, we can expect with a high probability, be careful, it's just a probability argument, that we get good results then. So white noise is a good idea. The white noise and frequency spectrum has what kind of spectrum? So the power spectrum, yes, yeah. It's flat. So all frequencies are there. So what kind of signal generates a flat signal frequency spectrum? Yes, the direct impulse. What do you do? And then we are back to my son. What do you do if you smash somewhere against it? It's the direct impulse. Well, he does it with his feet, and we do it in a different application. Just to move on to a practical application, we right now make measurements with robots which are coupled, and these robots are interlinked via a static link, and we want to see how the frequency spectrum is. And what do? We measure the spectrum by means of a spectrum analyzer and smash with a hammer against it to excite the system by means of white noise. So it works well. So you get the spectrum. I'll show you next time the results for a huge construction of this. Why we do this, explain then. But this is not sufficient because up to now we have consistency in the mean square if this holds, and now we can also calculate the estimation error which is given here and look for the expectation. And the interesting fact is, I move in here, we find out, okay, the expectation is equal to 0, but I wanted to look at the variance. Our interest is what happens with the variance of the estimation. And after moving through all these matrix manipulations are not so important at that point, you can read that at home, but the result is a little bit too fast here. Here you see the variance. The variance is limited. It's not infinite. That's perhaps the most important result. So the variance of the distribution of the difference between the measurement, the model parameters and our true parameters, which is theta tilde, can be calculated, what is done here on the slide. And it's just scaling the original variance value, sigma squared, with the input values. That's the interesting fact. So, but the most important part, it's not an infinite value. So we have exactly what we want to have. So, and the variance is limited. Second, we have to prove that the variance tends to 0 if the number of measurements gets bigger and bigger. And that's calculated here. First of all, you can look at U transpose U. You see it here. U transpose U is given by this super matrix. It's just a manipulation of the matrices. If you look at that, you find out that this can be easily, more or less, approximated with capital N times the autocorrelation coefficients of U, of the U values. So you get here the autocorrelation matrix at the time at tau equal to 0. And if this is regular, then you can see that the inverse of it tends to 0. So because U transpose U has to be inverted, which brings N into the denominator. And therefore, if N goes to infinity, the matrix fades away, more or less. So it's 0. So the variance goes to 0, the more measurements I have. So we have our consistency proof. This is interesting. Perhaps I should add this. Here, this is important. So in the limit, if N tends to infinity, bye-bye, and tends to infinity, by probability, we get 0 as a result because N is in the denominator. That's the result. And this is wonderful because the more measurements we get, the better the result is. The less the smaller the variation is. And second, and in this sense, we get a consistent result. And this is very helpful. And here's the estimation error, which is given here. And we can more or less approximate it by means of the cross-correlation coefficient of the matrix U inverse of times 1 over N. That's the result. And this is interesting. The second interesting fact is if you have disturbances with the variance sigma square at the output, and now we can look at two facts. One is we have almost small disturbances, right? So almost nothing. Say there's almost no variance in the disturbance. Then obviously sigma is close to zero, right? Consequently, the variance is also close to zero. What can we say about our number of measurements we need? Not so much, right? So the smaller the disturbance is, the easier I get the set of parameters out of it. And this is also, well, given by our intuition, right? If you, by intuition, you would say, yes, if there's nothing fluctuating at the output, I would expect that I get the result right away, just with one measurement. If I have a super precise measurement device, so I make one measurement and I'm happy. That's why in the lab equipment, you usually have the super expensive voltage meters and current meters, which are super precise, do not have fluctuations, etc., because you need not so much measurements. If you have a really old and whatever an ampere meter or so, which is fluctuating, has variance in its measurements, you need more measurements. Back to Gauss in its early ages, he realized that, and this is a proof according to Gauss, but now in the modern setting, but with the modern notation. But the original paper was written that way. So he realized, well, I just have to look at the planets as long as I can and do the measurements as much as I can, and then I will get out the parameters. It's just a question of yeah, doing the work. No? Okay. This is perhaps the most important part about that, and this is something you should already know. The question is whether you do. More or less. It's perhaps given in a different setting, but it's something in a different notation, but this should be something which is already known. The first step is always given, so we can be happy if we do that. We get consistent results under certain assumptions, and that is wonderful. Okay. Now I want to give you a geometric interpretation of the same thing. Have you ever heard this? No. Okay. Now, let's have a look, because this is something which I think is very important if you want to understand what's happening there and what is going on if I do this estimation thing. And the interesting fact is you can geometrically interpret the results in a simple way. So let's have a look. So remember, our parameter setting, the optimal parameters, theta m, are calculated by means of u transpose u to the power of -1, u transpose times y. This is the original setting, okay? So y times these matrices. And now I want to split the matrices a little bit. Now let's calculate the prediction of the model. So our optimal parameters times u gives the output value. So that's what we did before, how we got the parameters. So ym is equal to u times theta m star, and just inserting it, we get this. Okay, now I make an abbreviation. This pi u is just the combination of these matrices to get it a little bit more compact, that's all. Now, what we can write is pi u times y is ym. Okay. Now let's look at what happens. You can also interpret this here as a matrix multiplication with y. So it's nothing else than saying, okay, it's some sort of projection, right? It's some sort of matrix manipulation, which just puts what the matrix does, puts the same thing in a different basis, if you want. So a different way of looking at it. And we want to interpret this a little bit. For that, let's calculate E, the difference between our original values, Y, and the YM values. So easily be rewritten in Y minus pi U Y is 1, or the identity matrix, minus pi U times Y. There's a wonderful thing, which there's a slight mistake here. It should be U. If you take this matrix pi U with this orthogonal sign, if you multiply 1 minus pi U with U, it gives 0. And now we have the interpretation. What is it? So think of the entire thing here. You have the U values, U1, U2 in our case, as being the rows. And Y is something which cannot be represented by the U values. What we do is we take Y and project it into the plane of the U values. This is given here because the error itself is orthogonal to YM. That's it. So we have this orthogonal relation. We can also say we try to get the best fitting in that sense that we want to represent the original Y value, which can be also seen as a vector, to be represented with a basis which does not fit in the space of the Y values. This is the geometrical interpretation. And the best I can do to represent a vector which lives in a different space, so in a three-dimensional space, is to project it into the space where I can do anything, right? That's the best I can do. If I'm staying here and I want to look what's happening here on the floor, the best I can do is to project myself here on the floor, right? Then I get the best representation of it. That's what's happening here. And the best I can do, we know the smallest value between the plane here and this point is obviously the orthogonal direction where this orthogonal line hits the original Y. That's it. So it's quite simple to say, okay, it's this orthogonal projection of Y onto U1, U2, U3, etc. So that's the point. So with that, we can say the model output and the least squares residual errors are orthogonal to each other by looking at the various vectors. Just do the inner product. This is an important relation, which can, if you understand this, you understand almost everything of the theory of Kalman filtering, because it works similar to that. So perhaps just as a hint, if you want to understand deeply Kalman filters, you please go back to this simple principle, which directly starts with simple linear least squares. You just project in some sense. We don't want to do it here. You will do it in other lectures, but the principle is the same. And we are here to learn principles, by the way. This is one fundamental principle which is given. So what can be different, just to give you a hint to other domains? Here is the original school type or orthogonal projection you learned at high school, right? So you have a vector, you do a projection on a surface, this orthogonal projection. But you know already from your higher math classes in the first semesters, well, orthogonal things are something has to do with the inner product. So if I have an inner product which gives 0 defined, then I can define also this operation to be orthogonal to something. in different ways. So I can do it for functions, I can do it for matrices, I can do it for operators and this, and therefore, and these things, and therefore this helps to understand different methods. Please keep this in mind. It's not so important for the practical implementation, but it helps to understand other principles. It also helps to understand different, in other domains, different procedures. Okay, so now I want to show you that we can use this, right? Sometimes, just as an example, it's just an example to use this orthogonal projection. Sometimes, you have a super huge linear system and static linear system, and you're interested in just a set of the parameters, just a subset of the parameters, not everything. So, and if you're interested in the subset of parameters, then the following we can represent the problem as follows. Suppose you're interested in the parameter theta1, which consists of the entries theta11, theta12, etc., etc. And there are some parameters which you are not interested in, theta2. And of course, we have some noise which might be added. Now we have the vector-wise y values. And the question is, can we find theta1 without calculating theta2? Well, the answer would be, your answer can be, okay, I calculate theta1 and theta2, and then I have theta1. This is the engineering way of doing it. Now I give you a procedure which helps to reduce the complexity a little bit. Well, why not multiplying? So I go to the next slide first. Why not multiplying the left-hand side, from the left-hand side, the entire equation with the orthogonal complement pi u2? What happens? Again, here's a small misconception, should be u2. Then the following results. The only thing I did is I multiplied my entire equation from the left-hand side with this matrix pi u2 orthogonal. What do I get? I get pi u2 orthogonal u1 times theta1. It's the first expression. Pi u2 orthogonal times u2 times theta2, which is over here, hopefully. So to make it explicit. And the remaining part, I multiply pi u2 orthogonal with the disturbances, right? That's the setting. It's just expanded the expression here. Well, now the following nice thing happens. Due to the fact that pi u2 orthogonal times u2 is orthogonal on u2, obviously it gives 0. It's the inner product. It vanishes. That's it. So the remaining equation is pi u2 u1 times theta1 plus v times here. It's not a mistake. It's on the slide before, but I put it here for our convenience first. Sorry. Not transposed that way. So the question is, what's about pi u2 orthogonal times v? What happens with the projection of the disturbances of the original problem? And the interesting fact is that is given on the slide before, that first pi u2 times v is given to be I minus, I just multiplied it with the expression times v. This is the definition of pi u2 orthogonal, which then is v minus this one and that one. And with the consideration of the first line, you can see that for large values of n, pi u2 orthogonal times v gives exactly v. This is the interesting fact. So the disturbances for huge values of n fluctuate in the same way if I project them. This is a little bit counterintuitive, right? Because if you think something is fluctuating and you look at the same thing from a different perspective, which is something like wood projecting it, then this fluctuation remains more or less the same. That's what is given here. But the interesting fact is if the number of measurements are huge, then we have this fact. And then the following results. We have a equation which is similar to what we know. We have here a set of input values. Let's give them a different name. I write down output values, output new, okay? It's the same, which are given by the pi orthogonal u2 times y. And I get here a new u1 input matrix, which is given by this multiplication times theta plus some fluctuations, some disturbances. That's the very same we had before, right? It's the very same we looked at before. It's just a simple linear least squares problem. So, but instead of looking at the entire setting of theta 1, theta 2, we now just have to look at theta 1. But the difference is, instead of looking at the true output values, I have to project these output values in a different space and look at the different perspective on it. This is a principle we will use later in our lectures again. So therefore, please use and keep this in mind at that point. That said, we can finally calculate theta 1 m without the consideration of theta 2 directly by means of this, well, weird formula. That's not so important. For me, it's more important that you understand the principle. By projecting something into a subspace, it helps to reduce the complexity. That's it. Okay? With that, yes, so we have this point. Okay, one setting. This is, well, just to enlighten a little bit the situation that we can use additional, they can use the information and the knowledge about orthogonality of some of the vectors to each other to reduce problems. And I think it's important, therefore I mention that, because the procedure itself, it's implemented in MATLAB. It's implemented everywhere. So what you need to know for the future, to beat ChatGPT, by the way, is to understand the principle, to be creative later, right? So it's important to understand, okay, that's the basic principle. What happens if I use this principle? So, and that's something different than just repeating data which is already in the web, right? To produce something new. And as I already said, so I say this very often, that unfortunately large language models make your life more complicated. Why? Because your job is now to beat the ChatGPT part. Because everything which today, in today's exams and practical things, will be replaced by automation principles, so ChatGPT and other things which we already use. So, and your job will be more on the side to transfer the knowledge, to use the principles somewhere else, and to create something new. And if you ask me what is easier in terms of competences, well, it's just to repeat things, right? So therefore, it's the downside, but from my perspective, creativity is always nice. So it makes fun. We build something. So, but what you need as ingredient You have to understand this. And this is very often even more complex than just looking at the problem. Okay, so now I want to go to my last problem with the least squares topic today, which is the following here. Suppose the following. No, I come back to, I want to make a practical example to show you that. Think of the following. I think this is a really nice example. It's really old, but I think it's very nice. If you make airplane control, for example, the control of the height level control for the airplane to maintain a certain level, flight level, then there are control strategies. And my professor in control engineering worked in airplane control strategies. Different to what Mr. Inger said, in airplane control strategies, not the control engineer is testing his control strategies, but the test pilot. Okay. The automotive industry says, no, if they do something wrong, they should feel what they are doing. Okay. And this happens, by the way. If you have a wrong sign in your anti-slip control, you will rotate, of course. But it's not that problematic and dangerous like in airplane control. So what he did is the following. You know, if you fly on different levels, you have a different density in the air, and consequently, the flight dynamics is different. And the flight dynamics has to be identified. So the dynamics of the airplane. Yeah? And the dynamics of the airplane changes whether you fly at 100 meter above the ground or 1 kilometer above the ground, or even 5,000 kilometers above the ground. So what is going on there is a continuous identification of what happens. So you take the measurements of pressure levels, temperature, and all that. You have some structure, a sort of linear model, and you try to identify the parameters of the airplane. With that airplane identified model, you then automatically build control strategies by, for example, linear quadratic regulation, what we did in ODS, for example. Okay, it's exactly that. So you identify the system and then you do control. This is called adaptive control. So identification is the first part. And of course, to make it explicit, it's not so important how the temperature in Munich is if you fly to Hamburg and you're close to Hamburg, right? So therefore, the data which you captured around Munich is less important. And consequently, we should perhaps weigh the data in such a sense that the Munich data is not important, but the Hamburg data is important, right? So later data sets are more important than the older data sets, so to say. Therefore, one way of doing it is to weigh these data sets, and in such a sense that you have some sort of weighting matrices, or you can say, to make it directly explicit, and then I end my story here, you say, instead of using the sum of squares and you count every measurement in the same way, you say, no, the first is more important, the second is less important, therefore I have a weighting factor, W11, W22, and I can decide whether it's important item, yes or no. This also happens if you have outliers in your measurements, for example, right? So there's one spike which is popping out and you are sure this is a, well, wrong measurement. You don't know why, but it's wrong. And so you want to cancel this out, kick this out of your measurement list. And therefore, you have this weighting factors. And the question is, can we include this in our procedure of least squares problems? And the answer is yes. You see the result down below. I talk about this in a second. To end the story of my former professor, he's still living. not to its age, but when he did this experiment, he said in the he was in the airplane and engaged the control strategy with his adaptive strategy, but he made a sign mistake, and the airplane went down. This is not really funny because it was directly applied. So it really went down, and then the emergency button gets a really important button in the airplane. And the pilot, he was super cool. He told me that it was super cool and said, "Okay," it was Professor Graves, my predecessor here at the institute, also said, "Not so important. I have everything in my hand." And he said, he pressed the emergency button and well, get the airplane again flying, and he still lives. So at the end, this just to highlight that simple sign problems might be difficult. And now you're a master degree, and we have one. This is perhaps my last remark. In this sense, there's a different level. In the bachelor level, every mistake is allowed. In the master level, not. Please, if you're doing experiments, be aware of you are bachelor degree students, right? So you know what you do, and experiment with care always. That's important. I just want to highlight that because you're the one who's asked why something went wrong later on. What did you do? Did you do the right procedures, etc.? And if something went wrong and in this flight context, or Mr. Inger crashes into the side into pavement, or other people even worse, then he would be asked what went wrong, what did you do? And yeah, that's as a side remark. Back to our story here. So we can weigh this problem, and if we calculate the minimum of J in this setting, we get the optimal values in this sense. So we end up with theta m star in this sense. And the very difference is that U transpose WU to the power of -1 is similar to what we had before, but this only thing which changes is W, which is in between, right? So the weighting matrix. So with that, we can do exactly what I said and end up 5 minutes for that. What do you think? Yes. I make a starting point, that's all. I do not do the calculations. Just as a motivation. If you look at this nice formula, it looks at the very first glance simple, but from a computational point of view, there's a substantial drawback. Why? First of all, you have to invert matrices. And for you and for the computer, inversion of matrices is not funny. That's if the number of rows and columns grow. Then we end up with a problem. Okay, I have a matrix inversion. This is one problem. This is perhaps today with all the computer power not so problematic. But what is even worse is the situation if you get additional measurements, because this is the typical experimental situation. You make an experiment and you realize, yes, okay, I should do another experiment. Then you again have to recalculate everything. So remember my example from the flight control thing. Then of course you online have to recalculate this formula here every time you get a new measurement. And the question appears, does it make sense to recalculate everything from Munich to Hamburg? No. And the question is there perhaps something where we can reuse the result of the calculations before? And can we reuse our optimal estimation of the parameter setting before? And the answer is yes, it is possible. And the answer is given on the next slide, but I think we won't discuss this in detail today. I think we see each other next week, right? No, we don't, because I'm at the European Control Conference. That's why. So have a good week, and see you